Hello, so this should be the last video for dynamic programming. Just going to jump straight in because this follows directly from the previous one. Remember, there are 4 steps in developing a dynamic programming algorithm. We've done step 1 in the previous video. We have an optimal substructure, and now we're just going to show how to get the answer. And we're going to start by finding the recursive relation that gives you that optimal solution. So when we talk about the optimal substructure, we assume that we know what the optimal solution is. As in, we know which path to follow in the search tree. And how do we actually do that? How do you pick the subproblem that will give you the optimal answer? How do you choose? Well, just a reminder here, this is the problem that we had, rod cutting again. So the first table gives you the prices of the rod of length I, whereas the bottom one here, the bottom table, gives you the best value you can get out of a rod of length I. So this is assuming you cut it further. And if I look at the first level of the problem and subproblems relationship, these are the values that you can get. See, the most important thing here is for you to again notice that there's a difference between the value you can get out of a rod of length 4, like this one here, you can get $10. Why? Because you can break down further into 2 and 2, $5 each, versus the value of just a rod of length 4, which is $9. That's in the first table. Okay, so again, remember the rule: the leftmost rod we're going to leave untouched. We're not going to cut it any further. Okay, so now let's define this. Let's give some let's use some notation to define the variables that we have. I'm gonna say that pi is the price of the rod of length I. Well, that's exactly what we have here. And this optimal business, this optimal guy, I'm gonna call that Ri. So that's the maximum revenue that you can get if you have a rod of length I. Again, I is between 1 and n. Okay. So what are we doing? Like, if you have a rod of length n, you have like, what's Rn? So these are the things that you have to evaluate. Like this is the first level of like all the subproblems here, right? You will have the price of rod of length 1 plus the value from rod of length 4 and so on, and then price of rod of length 2, value of 3, price of 3, value revenue from 2, and so on. Like this is what we have. P1 plus Rn minus 1, P2 plus Rn minus 2, Pn minus 2, and so on. So all cases except for the first one, because that's here for length 5, then the Pn is just like, if you don't cut it at all, that's how much you're gonna get. There's no more subproblems, but all the other ones give you more subproblems. Actually, the second one doesn't give you more subproblems, because if you have a if you have a rod length 1, then actually that you can't. There's no more subproblems. So yeah, that's a slight mistake there. The first two do not create any more subproblems. So here is the recursive relationship, and it's actually very simple. Think about it. You go through all the subproblems, right? And you're gonna do pi plus Rn minus I. Well, Rn minus 1 you have to recurse because you have to work this out. But on that level, actually, you just go pi plus Rn minus y, and then you compare that for all different i's. So look at this picture again. You work out P1 plus R4, and then P2 plus R3, P3 plus R2, P4 plus R1, and just P5. You work all of them. You worked out all of them. You have to recurse if you have to, sure. But when you come back, you have all 5 values, or have 5 different solutions, and you compare which one is the best, and you pick the best. That's why we have the max function here. That's all there is to the recursive function in this problem. This is actually a very simple problem, and isn't that how you're gonna code it? I hope that's what you would do, right? If you see that kind of tree, how would you code it? Well, that's what you do. You worked out all the problems and then find the maximum. So generally finding the recursive relation is not hard, because you just go through all the options, you're brute forcing it, right? You brute forcing it, you go through all the possible solutions and you pick the best one. Pretty much what you would write in the code. So this is why I spent a week talking about brute force, because when you go to dynamic programming, there is similarities. Like dynamic programming is really just brute force in a smarter way, because you recognize the overlapping subproblems. Now, this week we're doing more, because I'm showing you that if you claim that you can do something using dynamic programming, then you have to be able to show the optimal substructure. But the recursive relationship, if you can write something using brute force, you can find the way to do that in dynamic programming as well. It'll be very similar in most cases. And the hard thing here is maybe writing what you have in your mind using mathematical notation, using the recursive relationship. For example, I have the longest common subsequence recursive relationship. And I don't know, maybe you find it scary, but if you go back to the first lecture, you look at the problem, look at how we break it down, you will see that that's exactly it. We're going to see more examples of this, I hope anyway. But every problem is different. So there's no really one way of doing this, defining this recursive relationship. It depends on what the problem is. And I think this is the hardest part. And if you work this out, you can code it. Right? Showing the optimal substructure property is a lot easier for me. That's how I think anyway. Because you just use the cut and paste argument that I outlined in the previous lecture. So no matter what the problem is, you just say the same thing again and again. Like, I have an optimal solution, right? Then if I don't have the optimal solution to the subproblem as well, then what I have is not optimal. That's it. But when it comes to recursive relationship, it's different every time. Okay, most of the time you're gonna see this whole you're gonna find the maximum or find the minimum. That's what's gonna happen most of the time. Maximum or minimum. But it can get tricky sometimes. Okay, so and like I said, if you already know the recursive relationship, you can write the code easily. We know now what is the recursive relationship. That just very tiny, very short. Rn equal to max of pi plus Rn minus I. So can you think of the code? Like, we've been talking about this for, well, hours maybe. Well, we've been talking about dynamic programming for a while. We haven't written any code. And I described this problem for a long time, for like almost an hour. So, how big is the code? This big. Seriously. That's the solution to the rod cutting problem. That's it. Because all you're doing is brute force. Again, this is why I think brute force is important for you. I mean, for you to learn how to write brute force properly, because dynamic programming is that you're still going to go through every single possibilities. You just storing it somewhere. So here, what am I doing here? If you're cutting a rod of length 0, return 0 because that's no value. Okay. Otherwise, what do? You're going to find the maximum of all these guys, and that's just your pi plus Rn minus I. Well, pi here gives you the price of a rod of length I if you don't cut it any further. So that's like the left side. And cut is when you recurse. You're calling the function recursively. That's really it. It's like 10 lines. So if I put those value p there, I think that's the value that we've been using. Yeah, I'll just extend this to like 30 just to see how fast it can be. You can definitely give it a try. Just copy and paste that. It will work. So here are the optimal answers. You can run it for n between 1 and 10 if you want to know. And these are the number of recursive calls. 1,000 calls, 33,000 calls, 1 million calls, 34. Wait. That doesn't seem good. That seems to increase exponentially. So what's going on here? I never actually stored the value anywhere. So this is what I did. This is brute force. This is working out every single possibility. And this is memoizing. So the difference is here, before I return the answer, I store it inside a table called R. And at any time, if R is already, if Rn is already filled in, then I just use that value. I will not recurse again. I will not keep on working out this for loop. Is that clear? Hopefully. Yep. Just something very simple. Just add one line up there, add another line down here. Well, inside of another line. Just make sure you store it inside a table and you're done. This is why I say top-down dynamic programming is simple. You just do brute force, and then you memorize the results that you get when you recursively do smaller and smaller problems. You remember the value that we get and put inside a table somewhere. That's how simple it is to do dynamic programming. So here it is again. That's the number of recursive calls, and you kind of see that this is roughly linear, almost. Maybe not linear, maybe more than n, but yeah, it's definitely, yeah, it's more. It's definitely not linear. Sorry, but I can imagine it's somewhere around n squared at most, probably less. I haven't really thought about what the complexity is. Shouldn't be too hard to work out. But yeah, that's the power of dynamic programming. You went from how big is it? 1 billion recursive calls to just 470 recursive calls. Right? So the code is there. Give it a try. But next, remember I mentioned that there is something better than top-down dynamic programming. It's called bottom-up dynamic programming. Not sure why I want to call it better. It's better in some situations, sure, but also a lot more trickier to write. So how do I come up with the bottom-up solution? So remember, by the way, we're still in step 3. We're still at the process of finding the value of the optimal solution. So we worked out the recursive relation. That's step 2. Now we're in step 3 because we can write the code. We can actually produce the value. And top-down, bottom-up, they're just two different methods of producing the same value. Okay, but let's see how we can develop a bottom-up solution. So, what do we know? If I want to compute Rn, I have to know Rn minus 1, I have to know Rn minus 2, and Rn minus 3, and so on. I have to know R2, I have to know R1, because I'm going to split up Rn. I'm going to split up the rod of length n to all these smaller lengths. So if I have to work out all of them, then why not just compute all of them like we did in Fibonacci? Right? So that's what I'm doing in this code here. I'm going to start with R0 equals 0. And then for all of them, for R1, so that's J here. So J is going to, there's a counter for R. So for R1, I'll work out all the possibilities and then find the max. See how R1 only depends on R0. So that's the inner loop. R2 only depends on R1 and R0, and I've computed them. R3 depends on R2, R1, R0, and they're all computed here. And this is, again, it should be faster. Okay, so this one I'm doing here in the code. Even if it's not faster asymptotically, at least it's nicer because it's just a for loop. It's not recursive, right? It's not recursive at all. It's just a for loop. So yeah, that's bottom up. Now the final step. We've done 1. That took the longest, right? 2. It's actually pretty easy. I still claim this is the hardest part, number 2. But in this case, it's actually pretty easy. Number 3, find the value of the optimal solution. You do this by coding it and then running the code. And finally, find the combination that gives you the optimal solution. So what we have now is, if you look at the code here with the bottom up, you know how much money you can get if you have a rod of length n. I'll return Rn. This is the answer. But you don't know which are the cuts, right? You just know that's the value. You don't know the cuts. So how do we work that out? So here's the final step. I'm going to show you the code first. And really there's only one line difference. I'm pretty sure there's only one line difference. So I have this array S here. This is going to hold the information of where I'll make the cut. It's not even declared inside this function here, so it's on the scope outside. A global variable, if you like, although there's no global variable in Java. Like, just we talked about that in the forum. Anyway, just a little aside. So just this S here is defined in a class somewhere. It's outside this function, and it's just going to store. Where I make the cut. To make it more clear, let's say you want to work out the optimal solution for Rn, and because you're going to compute Pn, sorry, this is the other way around. I should say Pn, Pn-1, Pn-2, P2, P1. You're going to compute all of them, and then you're going to choose one of them, the cut that you make. Let's say, oh, I'm going to make the left-hand side of size, the leftmost segment, I'm going to keep it at size k. Right, and then because pk plus Rn minus k gives me the best value. So that's what I keep track of. I keep track of k. So now I have the array of the prices. And I also have an array si that keeps track of the cut that I made. So for I equal to 10, for example, the cut is 10 and 0. As in, I don't make any cuts. So I'm going to store S10 equal to 10. And the optimal solution is just 30. Just use 10. For I equal to 9, the optimal cut is 3 and 6. So we saw S9 equal to 3. What it means is that when I have a rod length 9, I cut it to 2 pieces, length 3 and length 6, and I keep track of 3. Then with 6, what is the optimal cut? Well, with 6, the optimal cut is just 6. So I do a lookup here for 9, then I do lookup here for 6, and voila, I know that I have to cut at 3 and then 6. So let's say if I do 8, I know that I have to cut at 2. Then when I look at 2, sorry, that's a mistake. When I look at 8, I look at 2, so I know I'm cutting 2 and 6. So the next thing I have to look at is if I have a rod of length 6, and the answer there, I cut at 6. So the best answer is going to be length 2 and length 6, which should be 22. Yeah, I hope you can confirm that. I think that's right. Yeah, I'm pretty sure that's right. Sorry that this PI here, remember, this is the prices. This is not the optimal value that you can get. You can refer to that in the previous pages. I know I should probably put it there, but I forgot. So sorry. Alright, anyway, this is the code. So once you have the table S, you can just traverse, like you can find the solution using this. I'm just gonna put all the solution on the string. Just keep on adding to the string. So again, give it a go. Make sure you understand how this code works. I'm not going to explain how this code works. It's just simple. Yeah, but make sure you have an idea on how this works. Right. So these are some examples. And yeah, that's pretty much it. So you're not really learning how to code, because as you can see, the code is very simple. You're learning how to recognize the situation where you can apply dynamic programming. Like coding is something you've done in like the first 2 years of your degree. You know how to code. And the code, we're not going to do something super tricky in coding. This is not This is not really a coding unit. This is a problem-solving unit. All right, so you're not learning like nifty way of coding. Like I ask you to do simple stuff like maps, etc. But yeah, these are still basic stuff. So you learn how to find out if you can apply dynamic programming. Okay, so number one, see if there's an optimal substructure. Number two, go find the recursive relationship. And three, just code it. Again, bottom-up dynamic programming will be harder. It'll be better if you can work that out, but it'll be harder. Top-down is generally easy. Okay, so I think that's it for dynamic programming. We're going to talk about greedy algorithm next, and it's going to be pretty similar. So before you move on to greedy algorithm, make sure you understand this optimal substructure part well, because it's pretty much going to be repeated. Same with the recursive relationship, right? If you read the textbook, chapter 15, chapter 16, they're similar in many ways. In fact, previous offerings, they do greedy algorithm before they do dynamic programming. And I decided that I think it's better to do it the other way around. So we actually mimic the textbook more now. Yeah, I'll come back next week with greedy algorithm. So yeah, I'll see you then.